Hi guys, welcome back to my channel Pirai Academy. In this series of Turing interview question, today we are going to see about a question called Hungry Frogs. So given the position of all frog in array X and their respective trunk length in array S, okay, insert position is given in array Y. So this is the insert, okay. This insert is like a creature, okay. It is a creature like flies, not the insertion of elements, okay. You need to return array that indicate the maximum amount of insert the respective frog can eat, okay. So this is going to be a question. So it is basically an easy question. They will be given the trunk length and the frog position and the insert position. Now you want to tell them what are all the maximum amount of insert each and every frog can eat, okay. For example, see this input, X is equal to 1, 4 and 5. So this is going to be your frog position, okay. Now S is equal to 2, 3 and 5. So this is going to be your trunk length. Now Y is equal to 2, 3 and 5. So this is going to be your inserts position, okay. Now for this one, the position, the frog position 1, what are all the insert it can eat, okay. So its trunk length is 2, which means it can go with the trunk length of 2 to the left side or trunk length of the 2 to the right side. If it go to the left side, the trunk length or the position, like let me draw the number line. So initially it is at where? It is at 1, right? 1. So it can go up to 2. So it can go up to -1 or it can go to the right side of 3. Can you understand this? Now see here, this 2, whether it can catches the insert at second position. Yes, it can. Whether it can catch the insert at the third position. Yes, it can, because 3 is also included, right? Yes. Whether it can catch the fifth position? No, because 5 is not there, right? So that's the reason why we got the answer as what? Only 2 here. Can you understand this? Yes. Now just take the frog at 4. Now here it is 3, right? So the frog is basically at 4. It can go up to 3 to the left side, which means it will be 1, and 3 to the right side, which means 7. So this all elements are between them. So it will be 3. Can you understand this? Yes. Now frog 5 at position 5. So its trunk is 5, which means it can be go from 0 to 10. Yes. And these all elements are between 0 to 10. So what is the value? It will be 3. Can you understand this? Yes. Now see the second example so that it will be more clear. So this is the frog, okay, frog position, and this is the trunk length, and this is the insert position they have given. Fine. Now they have given there is only one frog, okay, frog at position 3. Now trunk of length 5, which means it can go up to -1, right? Because 3, then it will be 2, then it will be 1, then it will be 0, then it will be -1. So it is basically like, here comes 3, right? Now it can go up to -2. Whereas here it can go up to 8. Can you understand this? Yes. Now between them, what are all the elements that are present? 1, 0, then 7 and 5. So that's the way the output is 4. Can you understand this? So from this itself, from the question itself, what is going to be your brute force approach? Hope you understand the this question clearly. Now it's your time to just go with the brute force approach. If you don't know the brute force approach, just continue this video, okay. So let me take the new paint file. Fine. Now what is going to be your brute force approach? Tell me. The brute force approach is simply like, just take the frog position, okay, the frog position plus what is the trunk length, okay. This is going to be your right side. Now frog position minus trunk, this is going to be your left side. Can you understand this? Yes. Now it's it's your job to just traverse just traverse among all the inserts. Okay, just traverse among all inserts and just check whether any insert is in between this range with inclusive of this right and left. If it is so, then you want to count it. Okay, and at last you want to just append to the resultant. So by doing this, what is going to be my time complexity? I'll be giving the time complexity of the n into m. And what is going to be a space complexity? It will be O of 1 because you are using a resultant array, not the auxiliary array. Okay, fine. So, and also see here, the time complexity is what? N into m, which means it is like frog length, which means x into what is the insert array length? It is y. So len of x into len of y will be your time complexity. Hope it is clear. So this is going to be your brute force approach. Okay, now just see the code for this brute force approach. See here, it is pretty much easy. I want to traverse the each and every position of the frog. Okay, and what is the left will be the frog position minus the tongue of this frog length. Okay, now right will be plus the tongue length. Okay, now count will be initially 0. Now I am going to traverse one by one in the okay, now I am going to traverse along the inserts. Okay, now I am just checking whether any inserts is in this range. If the inserts is in this range, then I want to just count plus 1. Okay, then after finishing that whole traversal of the insert, now I want to append the count to the resultant, which is respect to the frog position. Okay, now return the resultant. That's it. Hope you understand this. Now we want to optimize this solution. We want to just optimize this solution so that it will be of efficient time complexity. So how we can optimize this approach? Fine. So just see here what we are just supposed to do. We are just supposed to do what are all the inserts that are inside the range of those frog position under the tongue length, right? We want to find what are all the inserts that are present in between those range. Okay, if I know what is the maximum number and what is the minimum number, then I will be subtracting them. Like see here, if I know that in the example, let me take the example. So this is the example, right? This is the example. Now see here, -2 up to what? Up to 8, right? Now if I know what is the element, what are all the element that are greater than -2 but less than 8, less than or equal to, so greater than or equal to -2 and less than or equal to 8, then that should be the value, right? Then that should be the value. So it is basically like, if I sort this array, it will be 0, 1, then it will be 5, then 7, then 9, then 10, then 11. Okay, if I found out this 7 is the immediate lesser value of this 8, and the 0 is the immediate greater value of this -2, then I'll be just taking the elements in between them inclusively, so that my answer will be 4. So by doing this, I don't want to compare each and every characters. I just want to know what is the immediate lesser value for the right side and what is the immediate greater value for the left side. Can you understand this? To do this, we will be going with the binary search approach. Hope you understand why we are going for the binary search approach. Because in binary search approach, it will be log n. That's the reason why we are going for the binary search approach. Okay, so let us see how we can find in the binary search approach. As of now, we know that if I found out what is the immediate lesser of the right side and what is the immediate greater of the left side, then I will be just taking the elements between them. So I want to make sure to do these operations inside the binary search approach. So first of all, we can see how we can find the immediate lesser value by using the binary search approach. Fine. So let me take any other example. Fine. Now let us consider the target value is 7. For example, okay, target value is 7. So 0, 1, 2, 3, 4, 5 going to be in this. Now here is L, here is U, the lower limit and upper limit. Now I'm going to find my mid pointer. So what is the mid pointer's formula? It is going to be L plus U minus L divided by 2. Okay. Now if I find the mid pointer, then it will be of 2. Now the mid will be 2 as of now. Okay. Now check whether this 5 is less than this 7. Yes, it is less than this 7 because this 5 is not equal to 7, but it is less than the 7, which means it may be my immediate lesser value. It may be my immediate lesser value, right? Yes. So I'll be taking a separate variable called answer. Inside that answer, I'll be taking this index. So what is the index? It is 2, right? So I'll be taking this 2. Okay, and I'll be moving my lower limit to mid plus 1. Why? Because I may get my target value in my right side, or I may get the immediate lesser value, the better immediate lesser value. Like if there is 6 instead of this 7, then I want to take that 6 as my answer, not this 5, right? So that's why I'm moving towards the right. Okay, now what is my mid? Now my mid will be updated here. Okay, now check whether this 9 is equal to the 7. No. This 9 is less than the 7. No. Whether this 9 is greater than the 7. Yes. Then I'll be going to the mid minus 1. The upper limit will be going to the mid minus 1. So upper limit will be here. Can you understand this? Yes. Now what is the mid? My mid is now 7. Oh, 7 is equal to 7. Then I want to return that 7 as it is. Yes, because the 7 is the best answer. Always the target is the best answer. If there is no element that matches our target, then only we will be returning the immediate lesser value there. Can you understand this? If instead of the 7 there is 8, then we will be just going again with the upper limit to mid minus 1. So upper limit comes here. Now upper limit is less than the lower limit. Now we will be returning the answer only. So the 5 will be returned if instead of the 7 there is 8. Can you understand this? Because of this 7, we will be returning the index value of 3. Regardless of what we have stored in the answer, we will be just returning this 3. Can you understand this? Now hope you understand how to find the immediate lesser value or the target value match. Okay, so we have a code for this, or logic is built for this. Yes, now it's time to build the logic for immediate greater value. Okay, so let me take the same example 0, 1, 5, 7, 9, 10. But now my target value may be of 3. Okay, maybe of 3. Okay, now I want to find what is the immediate greater value, right? Initially my L will be here, my U will be here. Okay, so 0, 1, 2, 3, 4, 5. So my mid value initially will be at 2. Okay, now whether this 5 is greater than this 3. Yes, it is greater than this 3. So it may be my immediate greater value, right? So I'll be storing that in my answer variable. So what is the index? It is 2. Okay, and I may get still better answer if I move my upper limit to mid minus 1 here. Can you understand this? See here, this itself the as of now immediate greater value. Then how can I get a better answer if I move to the right side? Can you understand this? Now what is the mid value? Mid value is 0. Whether 0 is greater than this 3 or equal to this 3, no. Then we will be just moving our lower limit to here, to mid plus 1. Okay, now what is the mid? Mid is 1. Whether 1 is greater or equal to this target, no. So it is absolutely a lesser value. So again I will be moving my lower limit to mid plus 1. Now this upper limit is less than the lower limit, so our condition is not satisfied. So we should be stopping here. What is our answer? It is 2. Can you understand this? So this is the logic behind immediate greater value or the target. So if there is any 3, if there is 3 here, then when I encounter this 3, then I will be returning the mid index as it is. Okay, because this 3 has a higher priority. Fine. So this is going to be your entire logic to find what are all those range. Okay. So now let us go here. Okay. Now, as I told you, here it is -2 to 8, right? For this -2, it is the left side, right? For left side, I want to find the immediate greater value. So the immediate greater value is 0. Immediate greater value is 0. So what is the index? 0, 1, 2, 3, 4, 5, 6. So my index will be of 0. Let me change color. So my index as of now will be 0 for the left. Now, what is my right? It is 8. So I want to find the immediate lesser value. So what is the immediate lesser value? It is 7, which lies at 3. So 3. So I want to take 3 minus 0 plus 1 is equal to 4. 4 is going to be your answer. Can you understand this? Yes. So to do this, we are going to sort the insert array first. Okay. Now you want to just traverse the frog position array. Then you want to do a binary search to find immediate greater and immediate lesser for left and right values. Okay, or else we can again tell this as immediate greater for left and immediate lesser for right. Okay, now we are just subtracting them, like we are just subtracting the immediate lesser value of right minus immediate greater value of left plus 1, and we will be just appending this into the resultant, and at last we will be returning the resultant. That's it. So this is going to be your entire algorithm. Now tell me what is going to be the time complexity. So this is going to be the important part. So what is going to be the time complexity? So it is going to be, let us take n is equal to length of x, which is means frog. Okay. And let us take m is equal to length of y, which is equal to insert. Okay. Then what is going to be your time complexity? It will be, first of all, m log m, because we are just sorting it using the merge sort algorithm, plus here we are just traversing n and we are doing a binary search operation on m, so it will be log m. So this is going to be your overall time complexity. And what is your space complexity? It will be O of, here you are doing a merge sort for m value, so it will be m for the auxiliary space used in the merge sort algorithm. So this is going to be your overall time and space complexity for this approach. Okay, now it will be okay. And it will be running successfully because it is much more efficient than n into m. Fine. So let us see the code for this also. See here. First, let us see the basic logic, then we can go for the immediate greater and immediate lesser. Okay. Now at first I will be taking the resultant and I will be sorting the insert array. Now I am just traversing to the frog. Now left is equal to what will be the left? It will be the frog position minus s of I, which means the thunk size, and here it will be plus the thunk length for the right. Now I will be appending what I am appending, immediate lesser of my right, okay, minus immediate greater of my left plus 1. This is going to be your appending value, or this is going to be the number of inserts the corresponding frog can eat. Okay, and I will be returning the result. Now let us see the code for this. So here comes the immediate greater code. First let us see the immediate greater code. So first of all, I will be assigning the L and U as 0 and the length of y minus 1, and then answer will be 0 initially. Now when my lower limit is less than or equal to the upper limit, then only I will be proceeding with this looping. Now mid will be found out using this formula. If my current mid value is equal to the left, then I will be returning the mid value there itself. Okay. If my mid value is greater than the left, then I will be taking the answer as the mid value, because it may be my best possible immediate greater value, but I am not sure whether there is any other better value in the right side. So that's the reason why I am just moving to the right side, like u is equal to mid minus 1. Now else it will be L is equal to mid plus 1. Now I will be returning the answer at the last. Now here comes the immediate lesser value. So here also everything is same, but here the LF condition, LF, the mid value is less than the right, then it may be the immediate lesser value. Okay, so that's why I am just storing it in the answer, but we are not sure there is best or still better immediate immediate lesser value in the left side. So that's why I'm just in the right side, right? So that's why I'm just making my lower limit to mid plus 1. Okay, now else I'll be taking the upper limit as mid minus 1. Now I'll be returning the answer. That's it. So this is going to be your overall code. Let me run this. See here, the corresponding output is there. Okay, fine. So if you want to know about these kinds of algorithm, just go and search in my YouTube channel, and there are plenty of videos using this binary search approaches. Still, I want to put some more videos on rotated sorted array, because that also asked in Turing. And if you really like this video, subscribe to my channel. Don't skip any videos in this playlist, because all videos will be helpful once you are appearing for the Turing interviews. Thank you.